Welcome to this lecture on cosmology and curved 3D spacetime. In this lecture, I want to summarize a little bit about what's going on with the cosmology of our universe according to the Big Bang theory, and point out some common misconceptions that arise when people think about the Big Bang, which usually have to do with the fact that spacetime is curved. So when people think about the Big Bang, they usually imagine some giant explosion, out of which come flying a bunch of galaxies, and we're left here standing in the middle on our little planet, observing that there are all these galaxies out there moving away from us. And the farther away they are from us, the faster they're moving. So that we observe that the velocity of these galaxies is proportional to their distance from us, their radius, with a constant that is the Hubble constant. Now it turns out that this part of the picture is true. We do observe that galaxies are moving away from us, and the farther away they are from us, the faster they're moving. But what's incorrect is this whole notion of some explosion and everything coming flying out of that. So let's erase that and talk instead about our modern cosmological notion that 3D space is stretchable, such that we can put ourselves in the middle of this little box here, and filling up space are all these galaxies that we observe. But then the entire box is expanding as a function of time, so that any distance r that we have is equal to some stretch, which we'll call a scale factor a, which could be a function of t, times some what we call a co-moving distance, or something, or some notion of distance that isn't stretching with the universe. And if everything's stretching, you can imagine that wherever you are in this cube, you will see everything moving away from you according to the scale factor, a. And because that scale factor multiplies this co-moving distance, galaxies that are farther away will be stretching faster versus time. And in fact, under this notion of how we find galaxies moving away from us, we can use that velocity, which is the derivative of distance with respect to time, is equal to the time derivative of a, which I will use Newtonian notation to write as a dot times r co-moving. And then we can use the fact that r co-moving is r over a to say that this is equal to a dot over a times r. And so you can see we've derived, using this notion of stretching space-time, the Hubble law, where velocity is proportional to distance, with h being the time derivative of a divided by a. So this is our modern understanding of how we find that all galaxies are moving away from us. And if you play this backwards in time, what it means is that the size of our universe was smaller and smaller the farther back in time we get. And just like when you compress air, it heats up. As we compress our universe going back in time, it's going to be hotter and hotter and hotter until in the very early universe, we had such extreme temperatures that we would call it the Big Bang. But there was no explosion. We just have the expansion of space-time, causing things to gradually cool off and galaxies to move away from one another. So the universe is expanding, but expanding the universe requires energy because there's a force that acts between galaxies, namely gravity, and moving galaxies farther from one another against the attraction of gravity requires energy. And the cost of that energy is going to be g times mass 1 times mass 2 over r. And this is a energy which is subtracted from the energy of the universe as we expand. Now, under normal Newtonian gravity, acting in a flat universe that we would call Euclidean would paint a picture that there's some center of the universe, galaxies are moving away from each other from that center, losing energy, and if they don't have enough energy, they would turn around and they would fall back in under that gravity, and you would end in some kind of crash, collision at the end of this expansion. But it turns out we don't live in a Euclidean geometry, and gravity is not Newtonian. Under Einsteinian gravity, from Einstein, the presence of a mass distorts space-time, such that straight lines no longer go from left to right across the page. They bend around the contour of the gravitational field from this object here. And the way this is sometimes drawn is like some rubber sheet which is bending down around this object, such that when something that follows straight lines, like light, comes in, it curves around the curved geometry here and ends up exiting at a different angle. So under Einsteinian gravity, space is curved. And moreover, what curves space isn't just mass. Energy, equivalently, because E equals mc squared, means that energy also curves space. And this is why we're not in Euclidean geometry. In this new geometry, 3D space itself can be curved, just as it can also expand. And this is where things get a little mind-bending. How does Einsteinian gravity account for the fact that given enough gravity, galaxies might expand away from each other up to a certain point, but then there would be enough gravity to pull them back into a crunch? If gravity is nothing more than curved spacetime, then how do we describe something that moves away from you and then turns around and comes back to you? Well, it turns out the way Einsteinian gravity would describe that is to say that space is closed. And because I don't have enough dimensions to draw in, I'm going to do a two-dimensional case of closed, which is you imagine yourself on the surface of a sphere. And on this sphere, you can start with two galaxies that are moving away from one another. Let's say this one starts moving in this direction, and this one starts moving in this direction. Now in 2D space, instead of moving along straight lines like you do in Euclidean space, you move along a great circle. And all great circles intersect at 2 points if they're not the same circle. So these galaxies could have started out next to each other here, and we would have called that point the Big Bang. And they start out moving away from each other, but at some point the curvature of their space pulls them back towards each other, and they end up recolliding over here in what we would call the Big Crunch. So in this 2D version of a closed universe, this happens because there's enough gravity to curve space back in on itself and close the universe. So if your energy of the universe, we'll call it energy density, if your energy density is high enough, you can close the universe through curvature. But in our 2D version, if you don't have enough energy density to close the universe, you could end up in an open universe. And then in the 2D version of open, your galaxies can start out together, but instead of recombining on the end of some curved geometry, they can slow down as they exit away from each other, but still never quite come together. So in this shape, this 2D surface, you can start out with two galaxies. They start at a Big Bang and they start moving away from each other, but they never recollide. They just keep moving farther and farther away from each other. And we call this an open universe. And right on the edge of being between closed and open is a flat universe, where galaxies can move away from each other, but there's just enough gravity such that they only barely can get to infinity. There's just barely enough energy for them to escape, but it would take an infinite amount of time for them to get there. And we call this a flat universe. So how can you tell if you're in a closed, open, or flat universe? If you're in a flat universe, the sum of the angles of a triangle are equal to 180 degrees. And that's normal Euclidean geometry. In an open universe, lines tend to diverge. So if I tried to draw a triangle between 3 points, I would find that in order to follow a straight line from one to another in a curved space, the edges of my triangle would curve inward a bit. So in this case, the sum of the angles of my triangle would be less than 180 degrees. On the other hand, if I live in a closed universe and try to draw a straight line between 3 points, because the surface of this sphere is bulging outward, I will find that following a straight line is actually following a great circle, which causes my lines to bulge outward from one another. And in this case, we'll find that the sum of the angles of a triangle will be greater than 180 degrees. Now it turns out that changes in angles that you observe can be very confusing. For example, if you're standing over here on the left side of the page, using your telescope to look out at space, and you see two stars on the sky, and you want to know how far they are from one another, this distance d. In a flat geometry, what you can do is measure the angle between those two stars as you observe it, and if you can figure out the distance to those stars, which we'll say r, then for small angles you can take r times alpha, and that'll be equal to d, again for small angles. But in curved space, you can see how this might be violated. You could have two different stars, again separated by the same distance d, but if you're living in an open universe, you'll see them separated by a smaller angle for the same distance d. Which means if you measure this distance r, you'll find that r times alpha is smaller than what d actually was. Now how can that be? Well, in 3D space, when things are curved, life gets pretty tricky. For example, if we asked what is the total surface area of points that are a distance r away from us in a flat universe, we would say that it's 4 pi r squared. And whatever angle we observe here corresponds to some fraction of the 2 pi radians around the circle, and that fraction is this distance between the two stars. But in an open universe, there's actually more surface out here than 4 pi r squared. There is 4 pi times r0 times the hyperbolic sine, sinh as we sometimes call it, of the radius divided by r0, where r0 is the radius of curvature of our space. Now if this were a sine and not a sinh, then for small angles, sine of r over r would just be r divided by r0, times r0 over here would just be r, and we'd recover the flat case, 4 pi r squared. But sinh is a bit bigger than a normal sine wave, and as a result, the surface area of this sphere out here is bigger than 4 pi r squared, which is why when our stars are separated by a distance d, we end up seeing a smaller angle, because observing from over here, there's still 2 pi radians around in a circle as we look around, but now, because we have a larger circumference of that circle, d is a smaller fraction of that, and thus we get a smaller angle. So we can't use r to convert angles into distances anymore. We need to use something different, and for this, astronomers have invented a term called the angular diameter distance, dA. dA is the thing that you multiply by an angle to get the correct answer, d. But as you can see, for an open universe, dA, the angular diameter distance, is going to have to be bigger than what r actually is. In this case, dA will be r0 times the hyperbolic sine of the distance r over r0. And by analogy, we can do the closed case. In the closed case, for a star is separated by a distance d, we're going to measure a larger angle. And this is again because the surface of a sphere of radius r in a closed universe is going to have a surface area that's smaller than 4 pi r squared. There's less space out there than you think there is. In fact, you'll find that there is 4 pi r0 times the sine of r over r0 squared. Now for small radii, sine of r over r is approximately r over r0, and r0 times r0 cancel out, and you get that this is just 4 pi r squared. But for large r's that are of order the radius of curvature, this sine is smaller than you think it should be, and you end up with less surface area on your sphere. By analogy, we'll find that the angular diameter distance in the closed case is equal to r0 times sine of r over r0. And of course, in the flat case, the angular diameter distance was just equal to r. Now up to this point, we've only been talking about the geometry of our universe, whether we're flat, open, or closed, which was determined by how much energy there was in the universe, whether there was enough to close the universe back in on itself, in which case we end in a big crunch. And if this were the case, then when we measure stars or galaxies, we would generally be overestimating the physical distance between them if we just multiplied the distance to one of those galaxies times the angle between them. In an open universe, one that expands forever, with galaxies getting farther and farther apart, there's more surface area out there than you think, and we would be underestimating the distance between galaxies by multiplying our angle between them times the distance to one of those galaxies. What we've not yet dealt with is the actual expansion of space. And the reason we need to deal with the expansion of space is that light from these galaxies, as it comes to us, takes some amount of time to get to us. And as that light is coming towards us, the universe continues to expand. So during the time that this light is traveling towards our telescope, these objects are getting farther and farther from one another, as are the photons, which are being stretched away from each other. And even the wavelengths of these photons are actually being stretched as they get to us. So if we want to know how far apart these objects were at the time that this light was emitted, we need to divide by however much the universe has expanded since then. And using the equation we had above, which was that the radius of something is equal to a times a co-moving distance, and we define a to be 1 today, and a was generally smaller than 1 earlier in the history of the universe, to get the actual physical distance apart that things were at some distance r from us, separated by some angle, we need to multiply in a, because a will be smaller at the time that they were emitted. Now the very last thing we need to deal with is r itself, because how do we compute r if, as we're observing these galaxies, they're not only being stretched apart from one another, but they're also being stretched away from you? As these photons are running towards us, the space between us and them continues to expand. And it turns out the rigorous way to define distance between objects under special relativity is to use a Lorentz invariant metric, which is often called ds. And ds measures intervals of space-time in a way that's invariant under the relativistic Lorentz transformations. And in relativity, we find that the correct metric that is invariant under Lorentz transformations is dx squared plus dy squared plus dz squared minus c squared dt squared. So in four-dimensional space-time, the way you measure the separation between two things is by adding up, according to the Pythagorean theorem, the x, y, and z components of your space and subtracting off the time component of your space, using c to convert that time into distance. And also, according to relativity, light traveling on straight lines means that for light, ds is always 0, which means that for light to travel some distance along the dx, dy, and dz directions, some amount of time has to pass, and the equivalent amount of time that passes corresponds to, as you might guess, the speed of light, c. So finally, the right way to figure out the distance between the observer and a faraway galaxy is to add up the steps that light took on its way from that faraway galaxy to the observer, and then account for how much each of those steps has expanded. And when we do that, we find that r is equal to the integral from t1 back to t0 when these photons were emitted of c times dt, the amount of time that passed, divided by a. And because we've divided by a, according to this equation, this must be a co-moving distance. So now we have a way of computing the radius to some faraway galaxy by adding up all the steps that light took on its way to us and dividing by the scale factor at each time so that we can add up how much co-moving distance was covered. And then finally, we can convert that co-moving distance back to a physical distance. And so what all of this means is, for this r that we'd been using over here for angular diameter distance, we should really be using the co-moving distance that we just computed here. And as you can see by the fact that we're multiplying back in an a at the end, what we end up with is a physical distance, not a co-moving distance, corresponding to the separation of these two objects. So here's the final answer. We have an angular diameter distance that's r co-moving times a. Another way of saying that, if you want to do redshift, because a is the same thing as 1 over 1 plus z, where z is redshift, the angular diameter distance is the co-moving distance divided by 1 plus z, or just multiplied times a. In an open universe, it's almost the same thing, but instead of r, we have to account for the curvature of the space and the fact that there is more than 4 pi r squared units of surface area in an open universe using this sinh function and these radii of curvature. And in a closed universe, it's the same deal, except for instead of a sinh function, we use a sine function. So those are the general solutions for the angular diameter distances for curved geometries. And we've generally covered how we deal with distances and angles in a curved three-dimensional space-time. We dealt with the fact that space can be expanding. We dealt with the fact that we have Einsteinian gravity, in which space-time is curved and can close back in on itself. And we dealt with the fact that in these curved geometries, triangles have possibly curved sides, which changes the sum of the angles in a triangle. And that gives us a formula for the angular diameter distance, which we use to convert the angles that we measure into actual physical distances between the objects that we're observing. Now before we go, I wanted to do one last fun little thing. Because human brains are not very good at doing 3D curvature, we often end up talking about two-dimensional curved surfaces, like the surface of a sphere. And it's tempting, when we talk about moving around on a surface of a sphere, to think about moving around on the Earth. And that can get us some intuition about what it's like moving around in a curved two-dimensional space. But there's one key aspect of even a curved two-dimensional space that living on Earth does not give us, which is the fact that light in a curved two-dimensional space would follow the curvature, meaning that if you were looking out from your vantage point on Earth, rather than having your light head off the edge of the horizon of the Earth and being able to look up at the sky, we would find that light should curve around along the surface of your two-dimensional surface. Meaning that if we actually were living in a curved two-dimensional geometry and we had a big mountain on the other side of the planet, we should be able to look in any direction and actually see that mountain directly. So if we were drawing a landscape of what we might be seeing, we could see some clouds in the sky, some trees, and a background mountain that you can see in every single direction, where here's the snow line of that mountain, here's the tip of the mountain, and here's the base of the mountain. And no matter what direction you look in, all lines of sight end on the polar opposite of your sphere, and so you would see that mountain in every single direction that you look. And in fact, if you were standing here holding a ball and asking how big does that ball look as you move it further and further away, and you were to graph that, which is to say the angular size of the ball versus distance away from you, you would find that the apparent size of that ball would get smaller and smaller and smaller as it goes away. But if you lived in a closed geometry like this, when that ball gets further away from you, it starts actually swelling, meaning that more and more of the lines of sight that you could look at, the different angles that you could look at, would end at that ball, which means that you would actually find that it would turn around and get bigger and bigger and bigger as it moved farther away until it would get essentially infinitely big once it gets a distance of pi times the radius of curvature away from you. Now that's pretty weird behavior. What it essentially means, if I were going to redraw this graph now using the new terminology we've developed, is that angular diameter distance as a function of redshift, which remember is 1 over the size of the universe, will increase for a while. Objects will look like they're an angle getting smaller and smaller, but eventually turns over and objects can look bigger and bigger even as they're moving farther and farther away, which means that to get the correct physical size, we need to have a smaller angular diameter distance to get the physical separation of our galaxies, or the physical size of this ball over here. And there are two contributions to that effect. One is whether we're in open or closed geometry, and the other is the expansion of the universe. And because this can intuitively be a little complicated to think about, I thought I'd go ahead and show you what it looks like to actually live in a open or closed universe. I'm not going to do the expansion of the universe, but what it would look like to be walking around in 3 dimensions in a 3D curved space. So let's start in a kind of a trippy universe where I've got a bunch of boxes. They're these colored boxes that are all rotating here. And they're laid out on a grid in this universe, so I can walk around through them, and I see them all on this grid, rotating around and moving around. All right, so here are all my boxes. Some are farther away, and I can tell that by the fact that they're smaller, and some are closer to me, and I can tell that by the fact that they're bigger. Now in a standard universe like this, I keep running around and everything seems to make sense. But I'm not in a standard universe right now. I'm in a closed universe. And in this closed universe, lines of sight bend as I get farther and farther away. So here I am with these cubes getting farther and farther away. And what I'll find is as they get farther and farther away, some of them can appear to be bigger and bigger. Because as I look farther away, my lines of sight are curving back, just like in this picture. They're curving back towards the same cube through different paths. So I see the mountain from multiple perspectives. In this case, as I get farther and farther away, some of the cubes get bigger and bigger. In fact, as I get close to the polar opposite of one of these cubes, it becomes enormous. Although you can see by the fact that it's not masking out these other cubes that are rotating around, you can see that this cube, which I've shaded red to indicate that it's very far away from us, is nearly on the other polar opposite side of this universe. And that's why it looks so huge. I can look into many different directions and they all curve back onto the same cube that has the same physical size as all the rest of the cubes here. And as I walk forward, you can see that here are those cubes and they're still all the same size. But as I back away, again, some of those cubes in the back get really large. And that's the fact that their angular diameter distance has been increasing for a while, but now is decreasing in a closed universe until they're essentially infinitely big as they approach the pole. So this is kind of an interesting example. Why don't I do another one in which we do an open universe? All right, so now here we are in the same place with the same cubes, but now we're in an open universe. So in an open universe, I have the opposite problem. As things get farther and farther away, my lines of sight diverge. There is more space out there than it appears there is, and as a result, as I get farther away from things, they look like they get really small as they go away. So now it looks like things are very far away from me because they look very small, but in fact they're really not that far away. It's just the fact that my lines of sight are diverging that makes them look small. So again, this is an open universe. In open universes, things look angularly smaller than they do in a flat universe. Finally, because we're doing cosmology here, I thought I'd lay out something a bit more astronomical in orientation, which is if I had a bunch of galaxies here, and you can tell the galaxies are in back by the fact that they're redder. And now again, I'm still in an open universe, so as I back away, these galaxies look smaller and they look like they get separated by less and less space, when in fact, they're not that far away. They're just getting smaller faster. On the other hand, if I move to a closed universe, I will see the strange case that even though these galaxies are quite red, they don't look like they're that far away. They look quite large. And as I continue to go farther away, these galaxies get larger and larger. Again, this is because they're approaching the far opposite side of the closed universe to me. And that means that almost every line of sight that I take here converges to one of these galaxies. What's particularly weird is that here's a foreground galaxy, which is technically the same size as this other red galaxy that's in the far background. So how is it that I can see past a galaxy of the same size to see this other galaxy in the background? Well, it's because my line of sight as I look off to the edge of this galaxy is curving around that galaxy and hitting the galaxy behind it. And that's what's making this other galaxy in the background look so huge. But as I walk forward, here are the galaxies again laid out. But as I get farther and farther away, some of them angularly look very large. And of course, this messes with your sense of perspective. It looks like things are moving towards you, but in fact, they're just getting bigger because they're approaching the singularity on the other side of the universe. All right, so that's all I have to say about cosmology and curvature of 3D space-time. We live in a very mind-bending universe.